Hello friends, I am Dr. Maninder Singh from Department of Computer Science, Punjabi University, Patiala. Today's lecture is on International Data Encryption Algorithm. In this lecture, we are going to discuss about the working of an international data encryption algorithm. Let's start. Cryptography, as we know, is the study of secret writing. Crypto means secret and graphy means writing. It is the science or art of including the principles and methods of converting an original message into one that is understandable and then transforming the message back to its original form. As the area of cryptography has made progress, cryptography today is believed as the study of techniques and applications of securing the integrity and authenticity of transfer of data under difficult conditions. In the field of networking, functions of network prevention or detection is huge. It is a very important tool which provides the protection from a variety of external and internal threats in any network. To support the network intrusion detection in a network includes the accomplishment of the security goals in the network, which are data confidentiality, integrity, authentication and non-repudiation. Cryptography is the science associated with providing secure communications. The aim of cryptology is to create schemes which allow only authorized access to information, that is, to prevent all malicious attempts to access information. Unauthorized access to information is determined by a cryptographic key. A user possessing the correct key will be able to access the hidden information, whereas all the other users will not have access to the information. Cryptology contains cryptography and cryptanalysis. The former includes the study and implementation of a variety of techniques through which information may be rendered unintelligible to all but the intended receiver. There are two types of cryptography: symmetric and asymmetric key cryptography. The symmetric key cryptography algorithms use a single key for both encryption and decryption. These are the most widely used schemes. They are preferred for their high speed and simplicity, where in asymmetric key cryptographic algorithms, two keys are involved: private key and public key. The private key is kept secret, while the public key is known to everyone. The encryption is done with the public key, and the encrypted message can only be decrypted by the corresponding private key. As we know that the use of internet is becoming broadly accepted these days, it has become a fashion of transmitting data over the network. However, people have found different methods to break the security of the data which has to be transmitted over network. Actually, there came into being a method to make our data protected against hacking, and it is known as cryptography. In the cryptography, International Data Encryption Algorithm, or IDEA, is one of the ciphers which encrypt the text into an unreadable format and makes it secured in order to send it over to internet. The International Data Encryption Algorithm, IDEA, is a symmetric key block cipher that was designed by Lai, Massey and Murphy in 1991. IDEA is an improvement of the proposed encryption standard PES that was designed in 1990 by Lai and Massey. PES was designed as a replacement for the data encryption standard ES, which was not secure enough. It is in fact a modified form of PES, which is proposed encryption standard. The new improved algorithm was called the Improved Proposed Encryption Standard IPES, and its name changed to IDEA in 1992. IDEA is a candidate block cipher to the new European schemes for signatures, integrity and encryption, the NESI project. It is a project within the Information Society Technologies IST program of the European Commission. First, unlike the ES, IDEA is patented, and therefore user has to obtain a license before it can be used commercially. Second, the ES has a long history as compared to IDEA. Although IDEA failed to replace the ES, but it was included into email privacy technology known as Pretty Good Privacy (PGP), which is a data encryption program used for signing and encrypting various text file version 2.0. Now, IDEA has been replaced, but it is still an optional algorithm in OpenPGP standard. IDEA has solid theoretical basis and it is very well known contestant among many traditional encryption algorithms which are proposed to replace DES. Design of IDEA is based upon 3 operations from different algebraic groups. First is bit by bit XOR, second is addition of integers using mod 2 raised to the power 16, third is multiplication of integers using mod 2 raised to the power 16 with the values between 0 to 2 raised to the power 16. Inputs and outputs are treated as 16-bit unsigned integers. These 3 operations are incompatible in the sense that no pair of 3 operations satisfies distributive law or associative law. Confusion is provided by the incompatibility of these operations, and the diffusion is provided by means of a structure known as multiplication or addition, MA structure. The MA structure is the basic building block of the algorithm. It takes 2 16-bit values derived from plain text and 2 16 bits sub key derived from the key as input. The structure is repeated 8 times in the algorithm. Next, we are going to discuss the basic principle of IDEA. As we know that IDEA is a block cipher like DES, it also encrypts a 64-bit block of plain text. The key used by IDEA is of 128 bits long. The algorithm contains 8 identical rounds and a half final round, also called output transformation. IDEA is a reversible, that is, same algorithm is used both for encryption and decryption. Today, due to the presence of 128-bit crypto systems like AES, IDEA has become outdated, but its algorithm has become a very useful teaching tool to help students bridge the gap between DES, which uses XOR but no algebraic operations, and AES, which needs understanding of algebraic operations on finite fields. IDEA uses algebraic operations, but in order to understand IDEA algorithm, it is required to understand modular addition and modular multiplication. Let us discuss the working of IDEA. The 64-bit block of input plain text P is divided into 4 16-bit subblocks. In this lecture, we denote these 4 subblocks as P1, P2, P3 and P4. In order to produce the ciphertext, each of these subblocks goes through 8 rounds and 1 output transformation phase. In each of these 8 rounds, several arithmetic and logical operations are performed, and the sequence of operations performed in these 8 rounds are same. In the output transformation phase, only the arithmetic operations are performed. When we start the process of encryption, the 64-bit plain text is divided into 4 equal size subblocks, and these subblocks acts as input to the round 1. The output of round 1 becomes the input of round 2, and the output of round 2 becomes the input of round 3, and so on. And finally, the output of round 8 goes as input to output transformation phase, the output of which is the final 64-bit ciphertext. As we know, the IDEA is symmetric key algorithm, therefore, it uses the same key both for encryption and decryption. So, the size of input plain text is 64 bits. As we know, there are total of 8 rounds in the algorithm and the input key consists of 128 bits. In each of these 8 rounds, 6 subkeys are generated from the original key and the size of each subkey is 16 bits. These 6 subkeys are applied to the 4 input plain text subblocks P1 to P4. Therefore, in the first round we will have 6 subkeys K1 to K6. Similarly, for the second round we will have subkeys K7 to K12. In the third round we will have K13 to K18 and so on. And finally, for the 8th round we will have subkeys K43 to K48. The last phase is the output transformation which uses only 4 subkeys, that is K49 to K52. The 4 outputs C1 to C4 produced by the output transformation phase is the final ciphertext, which are joined together to form a final 64-bit ciphertext block. As we know, there are 8 rounds in IDEA and each round consists of same series of operations which are arranged in 14 steps. These operations include multiplication, addition or XOR. In step 1, P1 subblock is multiplied with first subkey K1. In step 2, P2 subblock is added with second subkey K2. In step 3, P3 subblock is added with third subkey K3. In step 4, P4 subblock is multiplied with fourth subkey K4. In step 5, XOR the results of step 1 and step 3. In step 6, XOR the results of step 2 and step 4. In step 7, multiply the results of step 5 with subkey K5. In step 8, add the results of step 6 and step 7. In step 9, multiply the results of step 8 with subkey K6. In step 10, add the results of step 7 and step 9. In step 11, XOR the results of step 1 and step 9. In step 12, XOR the results of step 3 and step 9. In step 13, XOR the results of step 2 and step 10. In step 14, XOR the results of step 4 and step 10. The addition and multiplication operations in these steps is not simple addition and multiplication, but it is addition modulo 2 raised to the power 16 and multiplication modulo 2 raised to the power 16 plus 1. Modulo arithmetic is very much necessary in IDEA. If the results of arithmetic operation or operations performed on two 16-bit numbers contain more than 16 bits, then the modulo arithmetic is used to bring it back to 16 bits. In this figure, P1 to P4 are input blocks and K1 to K6 are subkeys. The output of this round is denoted by R1 to R4 and not C1 to C4 because this is an intermediate output and not the final ciphertext, and this output will be processed in further rounds. Next, we are going to discuss the subkey generation for a round or key scheduling. The key schedule of IDEA algorithm is very simple and easy to understand. The input key size is 128 bits and the encryption algorithm uses 16-bit subkeys. In these rounds, 52 subkeys are used in total. The input key is simply divided into 8 16-bit subkeys and follow this algorithm. Divide the key into 16-bit subkeys. So, we have 8 subkeys starting from K1 to K8 and each having a size of 16 bits, and out of these 8 subkeys, 6 subkeys K1 to K6 goes as input to the round 1. Then after round 1, take these 8 subkeys and rotate these subkeys by 25 bits to the left. After rotation, we get 8 new subkeys and 6 subkeys out of these new subkeys go as input to the round 2, and repeat the step 2 until the total of 52 subkeys are generated. Therefore, each of the 8 rounds makes use of 6 subkeys. So, a total of 48 subkeys are required for these 8 rounds, and the final phase, which is the output transformation phase, uses only 4 subkeys. That means a total of 48 plus 4 is equal to 52 subkeys are needed. These 52 subkeys are generated from an input key of 128 bits. So, in the first round, initially divide the 128-bit key into 8 parts having 16 bits each. These are the first 8 subkeys K1 to K8. This process is shown in the table here. Then apply circular left shift by 25 bits position on the 128-bit key and split the key again into 8 parts of 16 bits each. As shown in the table, this gives us next 8 subkeys, that is K9 to K16. Then repeat the step be until all 52 subkeys are generated. Subkeys K17 to K24 are generated by starting from bit number 51 of the original key. Subkeys K25 to K32 are generated by starting from bit number 76 of the original key. Subkeys K33 to K40 is generated by starting from bit number 101 of the original key. Subkeys K41 to K48 are generated by starting from bit number 125 of the original key. Subkeys K49 to K52 are generated by starting from bit number 22 of the original key. Next, we are going to talk about the output transformation phase. The output transformation is the one time operation. It takes place at the end of the 8th round. The entire process of output transformation phase is divided into 4 steps. In step 1, multiply R1 and subkey K49. In step 2, add R2 and subkey K50. In step 3, add R3 and subkey K51. In step 4, multiply R4 and subkey K52, where R1, R2, R3 and R4 are the outputs of the 8th round. As shown in the figure, a 64-bit value, which is the output of the 8th round, is divided into 4 subblocks R1 to R4, each of 16 bits, and 4 subkeys are applied here instead of 6. Assume that these 4 16-bit subkeys are K49 to K52. The output of this process is the final 64-bit ciphertext, which is the combination of the 4 ciphertext blocks C1 to C4. Let us see how subkeys are generated for the output transformation phase. The process of subkey generation for the output transformation is exactly similar to subkey generation process for the earlier 8 rounds. At the end of the 8th round, the key was exhausted. Hence, the key is again shifted by 25 bits. Post this shift operation, the first 64 bits of the key are taken and are called as subkeys K49 to K52 for the final output transformation. Subkeys K1 to K6 are used as the encryption subkeys for the first round. Subkeys K7 to K12 are used for the second round. K13 to K18 are used for the third round, and so on. K43 to K48 are used for the 8th round. The last round, which is the output transformation round, uses only 4 subkeys K49 to K52. During the decryption of the ciphertext, multiplicative inverse mod 2 raised to power 16 of subkey K49, additive inverse mod 2 raised to power 16 of subkey K50, additive inverse mod 2 raised to power 16 of subkey K51, multiplicative inverse mod 2 raised to power 16 of subkey K52, subkeys K47 and K48 are used in the first round, and the 8th round uses multiplicative inverse mod 2 raised to power 16 of subkey K7, additive inverse mod 2 raised to power 16 of subkey K9, additive inverse mod 2 raised to power 16 of subkey K8, multiplicative inverse mod 2 raised to power 16 of subkey K10, and subkeys K5 and K6. Let us discuss how decryption is performed in IDEA. Decryption in the IDEA algorithm is performed the same way as encryption, but the key generation process is different. Subkeys are in fact generated using combinations of multiplicative inverse, additive inverse, and original subkeys. Now, what is the strength of IDEA? IDEA uses 128-bit key, which is double than key size of DES. Thus, to break into IDEA, 2 raised to the power 128 encryption operations are required. IDEA is approximately twice as fast as DES and is also considerably more secure. Using a brute force approach, there are 2 raised to the power 128 possible keys. If a billion chips that could each test 1 billion keys a second would try and crack an IDEA encrypted message, it would take them 1013 years. Being a fairly new algorithm, it is possible a better attack than brute force will be found. When coupled with more powerful machines in the future, may be able to crack a message. However, a long way into future IDEA seems to be a very secure algorithm. Let's discuss some of the applications of IDEA. Today, there are hundreds of IDEA algorithms based security solutions present in several market areas, vary from financial services and broadcasting to government. IDEA algorithm is the name of an established, secure and widely applicable block encryption algorithm, which allows efficient protection of transmitted and stored data against illegal access by third parties. The basic criteria for the development of IDEA algorithm were maximum security needs along with easy hardware and software implementation for fast execution. The IDEA algorithm can easily be embedded in any encryption software. Data encryption can be used to protect data transmission and storage. Typical fields are audio and video data for cable TV, pay TV, video conferencing and distance learning. Sensitive financial and commercial data, email via public networks, transmission links via modem, router or ATM link and GSM technology. And the last one is the smart cards. So friends, this was all about international data encryption algorithm. Hope all the concepts are clear to you. Hope to see you in the next lecture. Till then, goodbye. Thank you.